In this video we're going to talk about counting and why counting is important in probability. Well, let's address that first. The reason counting is such an important part of probability and knowing how to count is because the classical approach to probability says if we have an event that we're interested in and we want to know the probability of the event, we need to count the number of ways in which the event can take place and divide that by the total number of possible outcomes for the experiment, and that is going to be the probability of the event. And this turns up quite often, actually, if you're playing cards, for example, or rolling dice, that sort of thing. Then these methods for counting or for assessing the probability are very, very important. But turns out there are lots of other ways, other times in which this sort of thing turns up. And so when it comes to counting, there's one basic rule that everything else is predicated on. And I know you thought when you were a kid that, and you learned how to count just by adding the next biggest integer, that you were good for the rest of your life. But it turns out that there's another method of counting that you really need to understand this. And the basic idea, the fundamental rule of counting, is that if I have, say, two different tasks that need to be completed, and I want to know the total number of ways that I can complete both of those tasks, I just find the number of ways I can do the first one, and 1, and the number of ways I can do the second one, and 2, and all I have to do is multiply those things together. And if I have more than 2 tasks, all I'm going to do is multiply all those things together. So what we need to do is say, how many tasks do I need to complete to do something? 1, 2, 3, 4. Let's say I'm going to make up a PIN number, a 4-digit PIN number for my debit card. I would say, how many choices do I have for the first digit in my debit card PIN number? And you'd say, well, there's 10 of those. Okay, how many choices do I have for the second number? Well, 10 again. And for the third, 10. And for the fourth, 10. So how many different PIN numbers can I come up with? We'll just multiply all those together and we get 10,000 different PIN numbers. Okay, that's the basic idea. So we're going to go through and expand on this idea, and you'll hopefully be able to see something that maybe you didn't see before and understand the power in numbers and in counting. So here's another example. SKU, stock keeping labels that are used by any sort of store, not just a hardware store. So these have 2 letters ranging from AA to ZZ, followed by 4 numbers 0 through 9. So you could ask yourself, how many unique SKU labels are there with this combination? And we can see what some of these things look like to help us understand a little bit better what's going on here. We have a hex head 6 centimeter bolt, box of 12. It's got this SKU AF1078. Lime away cleaner RT4855. So depending on how many products the store is selling, we're going to need to know how many possible SKU labels there are. And it's very simple. If we start running out of them, all we have to do is add another digit or add another number on the front. But this is what they look like. So how many ways can you do that? Well, I've got, and the way to think of this is I've got 26 choices for the first letter, 26 for the second letter, and then I've got 10, 10, 10, 10. So it turns out there's 6,760,000 unique inventory labels using just those 6 digits. So here's another picture of this. For the first item we're choosing, we've got 26 possible, A through Z, 26 for the second, 10 for the rest of those. So there's an important aspect or important way to count things when you cannot repeat the item or the number of when you can't repeat the choice that you made in a given location the next time or the next time. And that's what we call factorial. And the way to think of this is if we're going to take n items and we're going to arrange those in a particular order. And so we would say we've got maybe just 4 items, 2, 3, 4. And the idea is we would say, how many choices do I have for the first item? That would be 4. Now I can't repeat whatever that first item was because I've actually taken that item and put it in place. So how many choices do I have for the second? There's going to be 3. How many for the third? 2. And finally for 1. And so we're going to call this 4 factorial. The notation we use is the exclamation point. And the idea is we're just going to say take n products and we're going to line them up. Doesn't have to be products, could be students. How many students we have in the class, whatever it is, how many ways could we arrange the order of the students? Turns out to be n factorial. And the notation again is an exclamation point. So that's n times n minus 1, or n times n minus 1 times n minus 2, so forth, all the way down to 1. So in other words, there are n ways to choose the first, n minus 1 ways to choose the second. So if we have an appliance service truck, it's got to make 3 stops, A, B, and C. How many ways could we arrange those stops, or how many orderings are there? We've got 3 choices for the first one, 2 for the second one, 1 for the last one, and this turns out to be 6. Now factorials are very interesting, and we're going to use them quite a bit actually. And so this is an important concept that you need to make sure you understand. And there we have it, 3 factorial is equal to 6. So one step beyond factorials is what we call permutations, and a permutation is an arrangement in a particular order of r randomly selected items from a group of n items, and this is denoted by npr, sub npr, p sub r. And the idea here is that I'm going to say I've got n items and I'm going to select those. From those I'm going to select r items, and I want to know how many ways can I do that if order matters. And when I say if order matters, what I mean is that xyz is different from zyx. Even though it's the same 3 items, the order matters. So a good way to think of this would be if you had a class and you wanted to know how many ways could you select a class presidency that has a president, a vice president, and a treasurer or secretary. And so you would say, well, I've got 1, 2, 3, and let's say there's maybe 8 people in the class. 1, 2, 3, 4, 5, 6, 7, 8 people in the class, and I would now say, how many ways can I arrange these people? So I've got 8 factorial ways to do that. I've got 8 choices for the first one, 7, 6, 5, 4, 3, 2, and 1. And that's the number of ways that I can arrange everyone. So that's this n factorial right here. But it turns out that I don't care about the order of the last 5 that are not selected. So given any particular ordering, how many ways could I rearrange the ones that are not selected? And I'd say, okay, I've got 5 to choose from, so I've got 5, 4, 3, 2, and 1. And so this is going to be 8 factorial divided by 5 factorial. In other words, I do care about the ordering of these 3 over here. because XYZ is different than ZYX. If Peter is the president and John is the vice president and Samantha is the secretary, that's a different presidency than if Samantha's the president and John's the vice president and Peter is the secretary. Okay, so this is very important. It's actually going to, we'll do another video with an example that uses this permutations that should help you understand a little better what's going on with permutations. Not this video, the next video will be on that. So let's move on then and talk about what are called combinations. A combination is very similar to a permutation in that we're going to be selecting R items out of N items. But now, when we're talking about combinations, we don't care about the order. In other words, XYZ is the same as ZYX. So the way we can do this is we have what's called NCR, so n factorial divided by n minus r factorial. That's the same thing as what we had for the permutations. And then we're also going to divide by r factorial. So what this is telling us is we're going to say we've got our 8 students again, and we want to choose, let's say we want to choose a committee of size 5, for example. So we have 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 different ways in which we can arrange all of the students. And now we want to say how many ways can we choose a committee of size 5. So we're going to say, let's put a break right here, and now we've got 2 different groups. One has 3 members in it, one has 5 members in it. And so this is going to be my, the 5 member is going to be my committee, and the 3 is not going to be on the committee. And so I don't care about the order of the 3 that I'm not selecting. So just like with permutations, we're going to divide by the number of ways that we can rearrange those 3 people. And that says we don't care about the order over here, but we also don't care about the order on this side. So how many ways can we rearrange these 5? Well, we've got 5 choices for the first one, 4, 3, 2, 1, so 5 factorial. So this is going to be 8 factorial divided by 5 factorial and 3 factorial. Okay, so this is very useful in lots of different scenarios and settings. In fact, one of the places where this shows up quite often that people don't maybe realize is in a very popular game. And the version of the game that I like, or the name of the game that I like to use, is Guess the Secret Serial Number. We'll say Guess the Secret Serial Number. And Guess the Secret Serial Number is extremely popular. People really like this game. But how it works is we say something like, okay, I'm thinking of a 6-digit number, and you try and guess it. And okay, so there's some additional things that you need to know about this 6-digit number. So this last number here is something between 1 and, say, 39. And these 5 numbers are something between 1 and, oh, I don't know, let's just say like 65 maybe. And then I will say, well, I don't care about the order of these. Order doesn't matter. And so what I'm doing is I'm picking 5 numbers between 1 and 65, and I don't care about the order, and then I'm picking another number between 1 and 39. So this is just way back here at the very beginning when we said what's the fundamental rule of counting. We're going to count the number of ways we can do each of these steps and multiply those together. So we're going to consider this then as having you could think of this as having this is 1. So selecting these first 5 numbers, that's one step. How many ways can I do that? Well, I've got to break that down into 5 different steps. And then I've got another step calculating of picking this 1 to 39. So how many ways can I choose these first numbers? Well, there's 65 choices for the first one, 64, 63, 62, 61. How many choices do I have for this other one? There's 39. But I don't care about the order of these here, do I? So I'm going to divide by 5, 4, 3, 2, and 1. And believe it or not, this is an extremely big number. In fact, let's figure out what that number is. We're going to go over to Excel and get a new Excel spreadsheet. And we're going to say this is combin, combine. The first number is 65, and we're going to choose 5 of those. So there's about 8 million different ways to choose 5 out of 65 numbers. And now we're going to multiply that by the number of ways to choose 39 numbers, which is 1 of 39 numbers, which is 39. And we see that there are about 322 million different possible values that we could have for this quote-unquote serial number. So 322 million 135 632. That's a big number. And so if we were serious about playing this game, we would say how long should we expect to play this game until we win, assuming that the number doesn't change every time we guess. Or we could say what's the probability of getting the right number on our first guess, or on any guess. And so to get the probability, it's just going to be 1 divided by that number. Call that probability of winning. 1 divided by, I'm going to write it 65 choose 5 times 39. This 39, by the way, is the same as 39 choose 1. And so this is going to be some very small number. Well, what we've really described here is not just guess a secret serial number, but it's also known as the lottery. And you can see that this number 65 is actually bigger than the one that they currently are using. In fact, the number of possible lottery tickets currently is about 175 million, not 322 million. And so they can adjust how many numbers there are here based on what you have to choose, and it's not too difficult to see that the chances of you winning are so small that you definitely do not want to use this as an investment strategy. You know, maybe it's entertaining and you can get some laughs out of it, and who knows, maybe you'll win the lottery someday. But don't base your hopes and dreams on winning this, because the number is so big that chances are you're not gonna. It's gonna take, literally, if you played 10 tickets a week, literally you're looking at hundreds of thousands of years before you should reasonably expect to win this thing. Or maybe it's not hundreds of thousands. tens of thousands of years. So that's what I've got here for counting. Again, this is a very important topic, and we're going to use it when we get into chapter 6, when we talk about discrete random variables, and in other places as well. So I've got I think one more video following up on this one, looking at permutations and a very interesting example. And after that, we should be done with the videos for this week. Unless you have questions from the homework, in which case you can send me email and we can go over any of the homework questions that you might have. Okay, thanks. We'll see you later. Goodbye.